Hello everyone, welcome to our video presentation entitled as Assessment of the Heapify algorithm. Today, we're going to walk you through what Heapify is, how it actually works behind the scenes, how fast it runs, and why it's used in so many computer systems. We'll also show you a real-world simulation using a hospital triage scenario to make the concept easier to understand. After that, we'll trace the code, compare Heapify's performance with other data structures, and give our final evaluation. There's a lot to learn, so relax, enjoy, and let's get started.
So what is Heapify? Heapify is a key procedure used when working with binary heaps, which are special types of complete binary trees. In these trees, every parent node must follow a specific role depending on the type of heap being used. In a max heap, the parent must always be larger than its children, while in a min heap, the parent must always be smaller. So whenever this role is broken, such as after inserting a new value or deleting a node or even modifying an element, the Heapify operation is used to restore the correct ordering. And also the concept of binary heaps dates back to 1964 when Williams introduced them as part of the heap sort algorithm. So one of the reasons Heapify is important is its efficiency. It works in O log n time because it only needs to move down the height of the tree. So not through all elements, but also a binary heap is stored in a simple array rather than a complex pointer-based structure, which means Heapify uses very little memory while still maintaining good performance. And furthermore, the Heapify process works by comparing a parent node with its children. If the heap property is violated, for example, if a child is larger than the parent, in a max heap, Heapify swaps them and continues this shift down or percolate down process. So this adjustment moves the larger value upward in a max heap or the smaller value upward in a min heap until the heap property is fully restored throughout the subtree. So ideas about ordering between parents and children, as well as the techniques used to adjust values downward in priority chaos were later expanded upon by Knott in his work on algorithms and data structures. So in overall, Heapify ensures that a heap remains properly structured and ordered, allowing binary heaps to function efficiently for operations like sorting and priority queue management.
I am Semini and I will explain how Heapify works. Heapify compares a node with its child nodes. If a child has a higher priority and a max heap, the two swap positions. This shift down process continues until the node finds its correct place. Through this method, the heap maintains its structure and ensures quick access to the highest priority element. This behavior is what makes heaps suitable for real-time application where priorities constantly change. And now I will discuss the time complexity. Each Heapify operation runs in O log n time because its work depends on the height of the tree. What interesting is that building an entire heap from an unsorted array is actually On due to how Heapify behaves near the bottom of the tree where most nodes are located. Because of this efficiency, heaps are preferred in systems that require frequent insertion, deletion, and priority updates.
So good day once again. I am Mendez and I begin with the discussion part of Heapify. So Heapify is a highly suitable system that need fast and continuous priority updates like schedulers or emergency response mechanism. Because heaps are stored in arrays, they benefit from the good cache locality and avoid the overhead pointer navigation. Another important point is the build heap operations. Instead of inserting elements one by one, which would take O n log n, Heapify allows us to build the heap in O n time. This efficiency comes from the fact that nodes are near the bottom of the tree where least work is needed. That's why Heapify is not only theoretically efficient but also practical for large-scale systems.
day everyone, I am Geralao and with me is my partner Duran. Today, we will walk you through a Java program that builds a max heap using an array. We will explain each part of the code step by step so that by the end of this presentation, you will not only understand how the code works, but also why each line is important. A max heap is a special kind of binary tree where the largest value is always kept at the top, or the root. This is very useful in many algorithms and systems that need quick access to the highest priority value.
Thank you, Geralao. So let's start with the basic structures of program. The class is named maxHeap, and inside, if we define several static methods, using static methods allows us to call them directly without creating an object. Although at the beginning, we also import a Java util array. Although in this program, we don't actually need it. It's common for programmers to include imports when experimenting or extending their codes. The real focus of this class is not the import but the function that help us treat an array as a binary tree. So this is what makes the max heap representation efficient and easy to work.
Thank you, Duran. Next, let's look at the helper methods. Left, right, and the parent. These three methods are small, but they are very important because they define the structure of our heap. The method left int I returns 2 times I. This gives us the index of the left child of the node at the position I. The method right int I returns 2 times I plus 1, which is the index of the right child. Finally, the parent int I method returns I divided by 2, which tells us where the parent of a node is located. All of this works nicely because we are using one-based indexing. If you look at the array in the main method, index 0 is set to null. The actual numbers start at index 1. This is done on purpose, so the math for parents and children becomes very simple and intuitive.
Thank you again, Geralao. So now that we understand how we move around the heap, let's go to the heart of the program, the max Heapify. The max Heapify method. So the max Heapify method, this method is responsible for making sure that the part of the heap rooted at index I follows the max heap rules. So inside the max Heapify, the code first calculates the position of the left and right children. So by calling the left I and the right I, this one, then it assumes that the largest value is at index I and stores that in the variable largest. After that, it checks whether the left child exists inside the heap, meaning the index is less than heap size, and also it checks if the left child is not null. If those conditions are true and the left child value is greater than valued at I, the largest is updated to the child index. Similar process applied in the right child. The code checks in the right index. It's still within the heap boundary. Makes sure that the element is it makes sure that the element is not null and compares the value at the right child with the value of the largest. If the right child is bigger, then the largest update again. If after the comparison largest is no longer equal, uh, it means that either the left or right child has a larger value than the current node. In that case, the code swaps value at I and at the largest This moves the larger value upward. However, in this swap might cause a new problem lower in the heap, so to fully fix it, the method calls itself again, recursively on the index and the largest. So this repetition continues until the subtree properly arranged as a max heap.
So thank you, Duran. Now let's move on to the build max heap method. This method takes an array and turns it into a complete max heap. First, it sets heap size to a dot length, which is the number of positions in the array. Remember that index 0 is null, but it is still counted in the length. Then, the method starts a for loop from heap size divided by 2 down to 1. This range covers all the non-leaf nodes in the heap. For each index I in that range, max heapify is called. The idea is that we fix the heap property from the bottom up. By the time we reach index 1, which is the root, all the nodes below have already been corrected. This strategy is what makes building a heap efficient. Although it might seem like we are doing a lot of work, the total time to build the heap is actually O(n), which is very efficient compared to inserting elements one by one into a heap.
So finally, let's look at the main method. So where everything is put together in main, we create the integer array. Integer array name A. So here's the integer name A. So the first element at index 0 is null, and the actual data values starts from here in 1. So this again match our 1 base indexing design. So next we call the build max heap A. Here it is. So this call transform our simple array of numbers into fully valid max heap. After that, the program prints the element. So this program prints the elements starting from index 1. So the printout shows the internal array representation of the heap. Even though the printout does not look like a tree, visually we know that the logical structures follows the max heap rules. So the element at index 1 is the largest, and each parent is greater than the equal to its each parent is greater than or equal to its children.
So thank you, Duran. So understanding the implementation is very helpful because max heaps are used in many real-world applications. They play an important role in priority queues, scheduling systems, and sorting algorithms like heap sort. Once you understand this code, you will find it easier to understand those advanced topics as well.
So thank you again, Mr. Sonny. So to summarize, we have explained how the helper methods manage the index relationships. So how max heapify enforce the max heap property, how build max heap constructs how build max heap constructs the entire heap efficiently, and how the main method sorry about that. So how the main method brings it all together. So we hope that this step-by-step explanation made the program clearer and show you how powerful and elegant the heap data structure can be.
So once again, I am Sonny Geralao, and this is my partner Justine, Raine, and Duran, and this is our explanation for max heap. Thank you for listening.
Good day everyone, I'm Geralao and I will explain the Min Heapify program using our Java code. Our focus today is Min Heapify only, how it works, why it is needed, and how the code fixes a subtree so that the smallest value stays on top. By the end, you should clearly understand how Min Heapify uses child index formulas, comparisons, swapping, and recursion to restore the min heap property. Before we jump into the code, let's quickly define what a heap is. A heap is a complete binary tree, usually stored inside an array for efficiency. In a min heap, every parent node must be less than or equal to its children. That means the smallest value is always at the root, which is why min heaps are commonly used in systems that always need the lowest value first, like shortest job scheduling, Dijkstra's algorithm, or picking the next small task cost. Now, why do we need Heapify? When we insert a new element, remove the root, or change a value, the heap property can get broken. Heapify is the repair mechanism. Specifically, when Heapify fixes the heap property for a subtree rooted at a chosen index I, assuming that the children's subtrees are already heaps. So think of min Heapify as, I'll make sure node I becomes correct compared to its children, and if a swap happens, I'll continue fixing downward. Excuse me. Before we store the heap in an array, we need a way to find children quickly. This code uses zero-based indexing. For any parent at index I, left child index is 2 times I plus 1, and right child index is 2 times I plus 2. That's why in the code you see left equals 2 times I plus 1, and right equals 2 times I plus 2. This mapping creates a complete binary tree layout automatically. No pointers needed. Excuse me. Before min Heapify, our code includes a helper method called swap. It simply exchanges two elements in the array using a temporary variable. We need swap because when a child is smaller than its parent, the smaller value must move upward to keep the mean heap rule. Here's the idea in plain words. Swap is the action that physically moves values to their correct positions. Now, we explain the mean Heapify method itself. The method header is mean Heapify int arr, int n, and int I, where arr or array is the array storing the heap values, n is the heap size, how many elements we currently treat as a part of the heap, and I is the index of the node we want to fit. So step 1, compute children plus initialize smallest. So inside Heapify, the first thing we do is compute the child indices. Left is equals to 2 times I plus 1 and the right is 2 times I plus 2. Then we set smallest is equals to I. This is important. We assume the parent is already the smallest. Then we try to prove otherwise by comparing children. Step 2, compare the left child. Next, we compare the left child with the current smallest. But first, we check bounds. So left is less than to n. This prevents accessing outside the array. If the left child exists and the array left is less than array to the smallest, then we update smallest equals to left. So what does that mean? The left child has a smaller value than the parent or the current smallest. So the left child should become the parent. Step 3. Compare the right child. Then we do the same for the right child. Again, we check right is less than to n first. Then we compare array or arr to right to less than array smallest. Notice we compare the array smallest, not array index. That matters because the smallest might already be the left child. So we are choosing the minimum among parent, left, and right. Step 4. Decide to swap or stop. Excuse me. After both comparisons, we check if smallest exclamation mark equals I. If smallest is still I, that means the parent is already the smallest. So the mean heap property holds at its node and we stop. But if the smallest change to left or right, then the heap property is broken. So we swap the parent with the smallest child. So step 5, recursion to fix deeper levels. After swapping, the value that moved down may still violate the mean heap rule further below. So the code, So the code calls mean Heapify array and smallest recursively. This is how Heapify pushes down an element until it reaches a correct position. Recursion continues until either of the node becomes a leaf or it is smaller than both of its children. So let's do a short example to make it concrete. Suppose array is equals to 9, 4, 7, 3, and 8. If we call meaning Heapify array 5 and 0, parent is 9, children are 4 and 7, the smallest is 4, so we swap 9 and 4. Now array becomes 4, 9, 7, 3, and 8. Then we Heapify index 1 because 9 moved down. At index 1, children are 3 and 8. The smallest is 3. So we swap 9 and 3. Now the array becomes 4, 3, 7, 9, and 8. Now, index 3 is a leaf, so we stop. The subtree is now corrected under mean heap rules. One more detail. The parameter n is very important in many real applications like heap sort. The heap size changes over time. So n tells Heapify which part of the array is still active as the heap. That's why we check left is less than to n and right less than to n, not left less than array.line all the time. Mean Heapify fixes one subtree, not the entire heap from scratch. To build a full mean heap from an unordered array, we start from the last non-leaf node and go upward to the root. For a size n array in zero-based indexing, the last non-leaf is n divided by 2 minus 1. Then we call mean Heapify for I, so equals to n divided by 2 minus 1 down to 0. This approach is efficient in the standard method used to build heaps. The time complexity of one mean Heapify call is O log n, because the element can move down at the most height of the tree. In real-life systems, this efficiency matters because we can keep priorities updated quickly. So in a triage or scheduling setup, the smallest value, like the earliest deadline or lowest cost, stays available at the top. To summarize, mean Heapify ensures the subtree rooted at index I satisfies the mean heap property. It finds the smallest among the parent and its children, swaps if needed, and continues recursively downward. That's the core idea. Compare, swap, and repeat until the structure becomes valid. Thank you for listening. I am Sonny Geralao, and that is our main Heapify explanation. Thank you.